Okay, let's just dive right into this explainer. I want you to turn on your imaginary thermal vision for a second. Picture the room you're sitting in right now. But instead of just seeing the paint on the walls or the furniture on the floor, imagine you could actually see the invisible physics happening all around you. Because that's exactly what we're doing today. We're digging into the fundamentals of structural thermodynamics to figure out how heat actually moves through the buildings we live in.
I mean, we've all been there, right? You're huddled on the couch, totally wrapped up in a blanket, and you're trying so hard not to touch the thermostat because you know the heater's already running. But you still feel that mysterious, super frustrating chill in the air. So why is your living room always cold despite your best efforts? Well, today we're going to uncover the exact scientific phenomena behind it. Because trust me, it's not just bad luck, and it's probably not just an old furnace. It's literally fundamental physics at work, actively pulling the heat right out of your space.
Enter structural thermodynamics. Now I know, that sounds like a ridiculously dry academic term, but honestly, it's really the story of an intense, relentless battle for your daily comfort and, let's be real, your monthly energy bills. Basically, it's the physics of how heat energy moves into, out of, and throughout the structures we call home. It's an unstoppable flow.
So here's our quick roadmap for today's explainer. We'll start with the thermodynamics around you, then break down conduction, convection, and radiation, before wrapping up with how we build better thermal barriers.
All right, part one, the thermodynamics around you. So, the space you're in right now, it might feel completely static, peaceful, perfectly still. But to nature, well, your warm home is basically a giant anomaly in the cold winter air. And nature absolutely hates an anomaly. Energy is constantly, aggressively shifting from high concentrations to low concentrations, just trying to find some balance. In fact, there are exactly 3 distinct, non-stop modes of heat transfer attacking your house right now to find that equilibrium. They literally never sleep. So let's meet them.
Moving to part 2, conduction, or energy moving through solids.
Conduction is the direct transfer of energy straight through solid materials. You know when you accidentally touch a hot frying pan? Yeah, that's conduction. And that exact same physical process is happening straight through the solid structure of your home, just sucking the warmth right out of your living room. Think of it kind of like an invisible energy relay race. Heat gets passed molecule by excited molecule, right through your interior drywall, into the wooden studs, and eventually out into that freezing cold January air. It's this massive, continuous chain of microscopic collisions. And if you don't have something inside your wall to interrupt that chain, you're going to lose a ton of heat really, really fast.
For example, think about a traditional single pane of glass. It offers absolutely zero resistance to that molecular relay race. The heat just zips right through that thin, solid barrier. But look at modern double pane glass. It does something genuinely fascinating. There's this tiny gap of air, or sometimes an inert gas, trapped right between the 2 panes, and it creates a crucial thermal break. It completely ruins the relay race. The molecules in that gas are just too far apart to effectively pass the energy along to the outside pane. Boom, conduction stopped.
Okay, on to part 3, convection, which is all about flowing air currents.
So if conduction was all about solid materials touching, convection is the sneaky draft in your home. We all remember from basic science class that warm, heated air becomes less dense and naturally rises, right? Well, as that super expensive warm air escapes up through your attic or the upper floors of your house, it actually creates a pressure vacuum at the bottom. And what happens then? It aggressively pulls in freezing cold outside air through the tiny cracks around your doors and windows to replace it. It's essentially a continuous invisible conveyor belt that is constantly stealing your heat. This is why fixing unsealed structural gaps with modern airtight sealing is an absolute game changer. I mean, you can have the thickest, most expensive anti-conduction insulation in the world packed into your walls, but if you have unsealed gaps, convection will literally just bypass it entirely. You absolutely have to seal the building envelope incredibly tight to trap that air and physically shut down that conveyor belt.
Which brings us to part 4, radiation, or invisible solar heat.
Now, our third invisible character behaves totally differently than the first 2. It doesn't need solid molecules to bump into, and it definitely doesn't need flowing air currents. It actually travels across the absolute vacuum of space. We're talking about the invisible solar barrage of electromagnetic waves hitting your roof and windows directly from the sun. Now, in the dead of winter, we love this. It's free passive heating. But in the middle of a scorching summer, man, this incoming radiation turns your home into an oven. It violently pushes thermal energy inside and drives your air conditioning bills completely through the roof.
So how do we handle this? Well, standard dark roofing materials passively absorb that intense solar heat. They act like a giant sponge, soaking up the radiation and conducting it straight down into your attic. Not great. But reflective structural barriers, which are often installed right under the roof deck, act like a giant mirror. They literally bounce those electromagnetic waves right back up into the atmosphere. This drastically lowers your cooling costs because it stops the heat before it even has a chance to enter the structure.
And finally, Part 5, designing better thermal barriers.
Let's put it all together. Here is the ultimate defense strategy for your house.
A truly thermodynamically efficient wall requires a specific, layered approach working in perfect harmony. Step 1, an exterior radiation shield to reflect the sun's harsh waves right back away. Step 2, a thick, fluffy anti-conduction insulation layer to break up that molecular energy relay race we talked about earlier. And Step 3, an airtight anti-convection interior barrier to shut down those sneaky drafts. By combining these structural elements, you're simultaneously blocking all 3 modes of heat transfer, the whole shebang. That is how you keep your home perfectly balanced.
As we wrap up this explainer, I want to leave you with something to really chew on. We know how to build walls that fight the weather of today, right? But as global weather patterns shift, bringing way hotter, more punishing heat waves, and much deeper, longer freezes, the invisible thermodynamic battles going on inside our homes are only going to intensify. So, how will our understanding of building thermodynamics need to evolve as global climates become more extreme? It's an incredibly fascinating, vital engineering challenge, and one that's honestly going to define the future of how we live. Definitely something to keep in mind the next time you reach over to adjust that thermostat.